How's it going, everybody? So last time we talked about how to use these electrical devices and make them store stuff so that computers effectively have memory. And memory is obviously very important in a lot of applications. Pretty much any application that just doesn't calculate a number one time needs memory. So go check out that video if you haven't already. But now we have made it to the final section of the hardware, where we're going to build a full-on CPU. So let's do that with this level right here. The first thing we're going to do is build combined memory. So what this means is that we need to get registers, which is one form of memory, and then we need to get RAM, another form of memory, and then we just need to combine them. And we're gonna combine them like how a CPU does. So we're gonna use A to write X to the A register. We're gonna use flag D to write X to the D register. And then notice this is a particular one. Star A writes X to RAM at the address given by the A register. So this requires two components to work. So of course, there's three flags. That means there are three registers. And I guess technically the third one is RAM, so not really a register, but there are three components we need. Of course, the first one is controlled by A, so we'll designate this register A. This one will be register D, and then this one will be register star A, and technically RAM. That's why it's star. So of course we got feed X into all of these guys right here. And so my keyboard is kind of being a little bit weird today, so that's why sometimes it doesn't click. So we're gonna feed X in correctly, and then clock needs to be posting through all of them, because remember, clock is kind of like the synchronizer. It makes sure everybody's on track and nobody gets ahead. And remember, we need to look at this again. So write X to RAM at the address given by the A register. So that's why we need to pass in this to the output, because A is kind of feeding this in. And of course, A will just go up here. D will go to this register. Star capital A will be the output of RAM. So yeah, this is combined RAM, and just to make sure it works, let's just test this complex feature out for a second, because it kind of tests two at once. So first thing, we want to write at address 3 the number 69. Let's just say that. So first, we can't pass in 69 yet because we need to pass in the address 3. So toggle A on, and then what we're going to do is post the clock time, say go ahead, do it. And then, okay, A is now 3. So you can kind of see already in the RAM module, it selects 3. And then let's write the funny number 69. But then we got to turn A off, and then we got to turn star A on, and then post the clock again. Now you see 3 has the binary representation of 69 at that address. So yeah, this works. So this is the simplest possible solution. Let us go on to the next level. So now we're going to talk about stuff that we'll see later on in assembly, but it's worth knowing how this works in the hardware right now. And these are instructions. So they're kind of like machine code bytes. For example, you might see stuff like F4, E3, all of that. If you open up a binary executable, this is what's actually happening in the hardware level, which is you break it into bits, and then you kind of group them by either ALU operations, memory operations, and then condition operations. So in this case, we have a 15-bit system, but we're only using 10 bits. And then, oh, we're also using bit 12 or something, but you'll see that later on. For now, we're only using 10 bits, and we just follow the table. So we're gonna split the instruction first, because we need to get the individual bits out of the instruction. And then I see we already need an ALU. So we've built an ALU before, we've built a condition before, and then right now I don't see any memory module in the selected available things. So I'm assuming these guys just go directly into the output. So I'm just gonna quickly put them in there. So bits 3, 4, and 5, star A, D, A respectively. And then now we're going to deal with the ALU. So bits 10, 9, and 8 all deal with like I call them opcodes, but they're just operation flags. And then these special flags, so the 0 flag and the switch flag, and then of course X and Y. But notice there's a little thing down here that says Y should be A or star A depending on bit 12. So we definitely need a mux to kind of control that. So when bit 12 is 0, it is A. So that means star A is 1, and then D0 goes to A. And then, of course, what is actually controlling that? Of course, bit 12. So bit 12 is selected into the mux. And then the output of the mux will determine Y. X is just D as specified, so we'll just pass it in directly. All right, so and then we got the ALU done. Now we need the condition, so greater than will be bit 0, equal to will be bit 1, less than will be bit 2. But then we have this X. Does this X go directly down here? Pause the video, see if you can figure out where this X goes to. The answer lies in the instructions. So assuming you've paused and thought about it for a second, X is actually the output of the ALU because the condition checks if the result is greater than, less than, or equal to. You need to do something with the result first, and then you can make a decision. You can't just directly pass in the data. Otherwise, all of this won't make sense. So that's why if you look down here, the J flag indicates that the ALU output conforms to the condition specified. So J flag is actually the reason why we're doing this is because the J stands for jump. And when we do jumping assembly, we're basically comparing with the ALU. So yeah, that's kind of how that works. Again, you'll see that later. But for now, we have successfully completed this instruction level. So now we're going to move on to the next level, which is the control unit. So the control unit is another very, very, very important unit inside the CPU. I told you the ALU is the one that's actually doing calculations, but the control unit is the one that's responsible for even telling the ALU what to do in the first place. So that's why we're going to have to build the control unit in order for any CPU to work. So I've had people tell me that the control unit and the ALU, pretty much just these two components make up the CPU. And we'll see later on in another level once we actually build a full processor. It's just basically clock, control unit, and then ALU. But again, I'm getting ahead of myself, so let's get the control unit done first. So bit 15, if bit 15 is 0, it's data instructions, otherwise it's ALU. For ALU instructions, the output should be as specified in the previous level, so we'll keep everything the same. For the data instruction, the output R should be the I input, and the destination should be the A register. So we gotta keep that in mind. So we need a splitter. Of course, we already see that we have 0 and 1, so we definitely need a splitter to kind of get the 15th bit. So that's why I have this right here. And then, of course, we'll get the ALU instruction because for ALU instruction, it's just specified as follows. So we'll get I down here, and then A will just pretty straightforward stuff, and like not really too bad. Just pass in them, match the input output, connect the dots. And then the output is kind of like where it gets messy because what we're going to do is first we're going to need a few selectors to address kind of like what's going on here with the bit 15 stuff. So bit 15 will definitely control these selectors, and again they will toggle between the ALU or the data instruction. So when in this case, A should be 1, D, A star, and J should be 0. So that means this something down here will have to indicate that A is 1. And of course, when we need a constant voltage, we'll just invert ground. So that's what that 0 stands for. So get inverter. Oh, by the way, I've formally put the inverter just for again just for clarity, but you can just get the inverter with an empty input because technically that's basically ground. So we can just do this. So we'll put inverter here, and then everything else will go through the the ALU instruction. So this will go to A, and then this guy right here will go to R, because again, if you look down there in this paragraph, this is what's kind of going on. So now we got these two boxes selected, and then so okay, another thing we need to do with these muxes is that the instruction, keep in mind, controls that as well. So that's why we need to pass in D0 to the instruction. So now we're just going to need a few AND gates. So sorry, NAND gates. I keep on getting these two guys mixed up, but we're going to need a few NAND gates to finally address what's going on here. So we're going to need a few NAND gates and then a few inverters to make it conform. So first thing is this NAND gate will go to bit 15, and then what this will do is this will address what happens to D. So this data pin will go here, see what happens there. This NAND gate will control that, and then finally we got to pass it to the inverter to make it an AND, because NAND by default is the opposite. So we will pass it into the inverter, and then this will go to instruction D. So just like that. Again, my keyboard and mouse are kind of finicky, so that's why it's not it's kind of delayed. And then we'll just do the same for the rest. So we need another NAND gate, and then whoops, and then another NAND gate, and this NAND gate again exactly same thing. Just we fetch from bit 15, see what's going on there, and then we'll look at star A, pass it into the inverter. So we need another inverter here, and then this goes into star A. This NAND gate will address what happens to J. So same thing right here. J gets passed in. Again, kind of the mouse is kind of being weird. I don't know why it's not. There we go. It's I kind of see now the wire's kind of off center. So there we go. We gotta make sure it's highlighted. And then finally inverter. This will make sure all the outputs are correct based off of that ALU instruction component right there. So pass all this in, of course, R, and we're gonna get A down to this mux here. R will be this mux, and then hopefully it will work. So let's check solution. There we go. That is the solution for this control unit level. Now we have finally reached the final level, which is a computer. So this is basically the actual microprocessor CPU that we have to build. And notice there's not really any inputs or outputs because CPU is its own independent thing, and there's not really anything that needs to go in. It can run stuff by itself. And by the way, this is not purely CPU because I realize that CPU does need input output. This includes RAM, so it's basically a computer. So let's see what we need. A control unit specified here. Storage memory, RAM, and registers. So we need RAM. I guess they just call it memory because yeah, that's the combined memory that we literally just did. We need a clock because the clock again keeps things going. A ROM unit to store our program because we need to write instructions for it. By the way, that's kind of like the next thing that's coming up after the hardware series. We are going to go into software and see how all that works. So stay tuned. And then we need a program counter. And this was built all the way back, but this is useful because it needs to go through the ROM and actually execute each one. So I see the ROM is already pre-populated with a basic instruction. So if we can make this work, that would be great. All right, so this seems a bit overwhelming. There's like a dozen of inputs all over the place. So first thing I recommend everyone do is to connect the clocks up because the clock, of course, will always synchronize. It's just it doesn't have logic basically. No logic gates. It's just a quartz crystal. All right, the next thing we need to do is figure out where the control unit goes because the control unit is basically going to interface with memory. So I'm assuming we need to plug these guys in, and then yeah, because the control unit decides what to do with it. Keep in mind we're not directly feeding stuff inside from the control unit. We're feeding what's the memory comes out. It gets processed by the control unit. The control unit does stuff with it because the ALU is inside there, and then it either decides to execute it or it just decides to store it back in memory. So that should be the connection for that. J is actually going to be responsible for the address of ROM because it's a jump instruction. So actually, the address of the ROM is actually controlled by the counter because I just realized the counter ticks up. So the J instruction is going to be the jump flag. So it's either going to set it into X, otherwise it's just going to use the program counter's output. Now, where does the ROM go? Well, the ROM feeds in instruction, so that's why we need to kind of like bring this all the way there. I know it's kind of getting messy, and I'm going to try to move the components around so that you guys can see what's going on, but it's still a bit messy. Yeah, it gets cluttered up here, but just know everything's plugged in except for X now. So we're just going to need to finish up X. So X is going to be the return value of the control unit. That's what this R is for, because that's kind of like the result. And then last of all, we need A to also be the input for X for the counter because A is kind of like the address here. So we need to pass A here. And that's again to deal with this guy because if the jump flag is on, then the PC should be set to value on A. And by the way, PC stands for program counter. That will come back a lot But look, when we're running stuff inside, the program counter is stepping through, and the clock is kind of doing its own thing. So yeah, if you see something like 4.2 gigahertz, that's literally 4.2 billion clock cycles per second. So it's happening way faster than I'm doing this right now, but this is basically a computer. All right, let's check solution. Let's make sure we got it right. Yep, and this is the simplest possible solution. They duplicate it a lot, so there's a lot of NAND gates in here, but again, just a computer just requires a lot of stuff. The next level is a bonus level because once again, we build a computer that can run instructions, and early microprocessors kind of did that. Like I believe even now Arduinos do that. You just flash stuff into the ROM, make it run. But that's kind of boring. Even Arduinos needs stuff like input and output. So that's what we're going to do in this bonus level here, which is actually look at how to do input and output. So assuming these input down here is stuff coming from the computer and the output goes back into the computer. Because keep in mind, we're kind of in the perspective of an inverted relationship. So the output is actually into the computer and then the input is out of the computer because we're external. We're outside the computer right now. So first thing we want to do is just the input state is where the button is shown in bit 15. Otherwise, it should be 0 if it's not pressed. So again, once you see stuff like bit 15, always just think to yourself bundler or splitter. In this case, it's bundler because the button is 1 bit. So just pass that in. That completes the input circuit. You can see it kind of works right there. Turn that on or off. Doesn't really matter. Now let's look at the lamp. So the lamp is actually just a 1-bit device, so not really that impressive. But you can think of it as a screen, like your display screen that you're watching YouTube right now. This could be lamp. Of course, it's not that it's going to be more complicated than NAND game can allow. So that's why we're just going to do the lamp here. And for bit 1 is on and then bit 0 is off, and X is controlling that. So now we can do this, but keep in mind this X and store stuff is coming from the CPU. So what we just built in the previous level, that's what these guys are. So what we need to do is we need to utilize the clock to make sure the screen gets refreshed on time. That's where frame rate and stuff comes in. Again, not really the whole story, but that's kind of like where it begins to happen. So the store will be set to A of this NAND gate, and then we need a mux to kind of control here. So actually, before we just directly pass X in, we need to control because again, input signal should be readable immediately, and then we use the clock to kind of cycle through that. So this actually goes to the splitter, the output of this, and X will be the input. Otherwise, it's going to be NAND. So this kind of toggles it in between. If we set something like 1402, then bit 1 is on, the lamp is on, and then we press the button. Obviously, I already showed you that. So yeah, let's see if this is right. Let's see. Okay, so we do have something wrong, of course, and this just shows that I'm kind of walking through this again. I don't have the solution on another screen because otherwise that's boring. I want to walk through the process with you guys. So I thought I did this right as I remembered, but clearly not. Let's see what happened. So set bit 0 to 1. Expect the on input to lamp when on to lamp to be 0 when so store is 0 but was 1. Because keep in mind this read only bit here kind of controls that. So when we toggle the clock, it is let's see. So ST is 0 and then expecting lamp to be 0. So let's see what this is happening right here. So on is 0, on is bit 1, but it should be 0. This should not be flowing through. I think what will happen is what we need to do is, oh, well, of course, this is a selector, not D1. I misclicked. So that's why that was happening, because it's feeding this all the way in. So yeah, that's a live debugging session right there. Let's make sure this is right. Yeah, and this is right. So you just kind of saw a live debugging session with me there. Again, I kind of did this, checked the gates, make sure all of that worked, and clearly I misplaced this gate into select. I got to place it into select instead of D1. So that makes it work. All right, so that completes the hardware section. Now you kind of know how to build a CPU from scratch, basically. The next section will still stay on NAND game just for a few more levels. We're going to look at machine code. So we're going to switch over to software. We've already built a fully functioning hardware, processor, and input and output like you see on the screen right now. But there are more things to come, and that will be, again, in the next episode, so stay tuned.